So this chapter deals with the topic of thermodynamics. And as you can see on the screen here, um, the main topics that will be covered in this chapter are entropy, free energy, and how they're related to equilibrium. So let's talk about spontaneous processes. What do we mean by this term spontaneity? Now, in everyday language, whenever people talk about spontaneity, people think about something kind of explosive or um, very dramatic or whatever. But that's not the case when it comes to chemistry or physics. When we talk about a spontaneous process, we're talking about a process that will take place without any assistance from anybody or any active role being played in order for the process to take place, right? So here are some examples of spontaneous processes. The waterfall runs downhill. A lump of sugar dissolves in a cup of coffee. At 1 atmosphere, water freezes below 0 degrees and ice melts above 0 degrees. Heat flows from a hotter object to a colder object. A gas expands in an evacuated bulb. Iron exposed to oxygen and water forms rust. So in each of these cases, they will simply occur. There's nothing that you need to do in order to help these processes to take place, right? So as stated down here, spontaneity is the notion of whether or not a process can take place unassisted without any help from anybody um, making sure that the process takes place. So if you look at the photograph to the bottom right side of your screen, you'll see a dramatic, well, a good example, I should say, of the difference between a spontaneous process and a non-spontaneous process. So we have the skier going down the hill on his skis, and that's spontaneous. He doesn't need to do anything except just, stand in the skis and basically he goes downhill, right? Now, what would be non-spontaneous would be the skier going up the hill, right? Because in order for the skier to achieve that, he or she would have to employ some energy on his or her part in order to ensure that they go uphill. So, that's basically the difference between a spontaneous and a non-spontaneous process. A spontaneous process will take place unassisted, while a non-spontaneous process would take place with some assistance, right? So let's look at this other example. So let's say you have this vessel, two vessels actually connected by a stopcock, and you have a gas trapped in one half of the vessel, right? Now we know from everyday experience what would happen if we open a stopcock, right? We simply have the flow of gas from the one that is filled with the gas, the flask that is filled with the gas, to the other flask until basically the gas takes up the entire volume of the two flasks connected to each other. So basically going from here to here is an example of a spontaneous process. Now the opposite, of course, is highly unlikely to occur, and therefore this is said to be non-spontaneous, all right? And in fact, in order for you to do the opposite, you'd have to expend some energy in order to get all the gas molecules back into the original flask from this state right here. So that's another example of the difference between a spontaneous and a non-spontaneous process. So this brings us to the question, how do we predict um, whether or not a process will be spontaneous, especially in the context of chemistry, right? Well, this is what was discovered, right? When it comes to spontaneous reactions, there are a couple of things that are noticed. One of them is that in most cases, the enthalpy of the reaction is relatively large and negative, right? So these are two examples of spontaneous processes, and you'll notice that they're both exothermic, all right? Um, However, you can also have this being spontaneous, but delta H is positive. And what is observed in such instances when the reaction is endothermic, that it is the size or magnitude of delta H is relatively small, all right? Here's another example of an endothermic process. Again, you'll notice that it is endothermic, it's spontaneous, but delta H is relatively small, all right? So in most cases of spontaneous reactions, the delta H is either large and negative or small and positive, all right? Um, so that's basically what is usually the case. But it turns out that their enthalpy is not the only factor that you can use to make a prediction as to whether or not a reaction is spontaneous. As we said before, usually the enthalpy for spontaneous reaction is neither negative or small and positive. The other factor that drives reactions, that makes reactions spontaneous, is a thermodynamic quantity known as entropy. So we need to spend some time talking about what entropy is. So what is entropy? Entropy, which is symbolized by the letter S, traditionally, is a measure of the randomness or disorder of a system. So the more random or disordered a system is, the greater is its entropy. Okay, so the greater the order, the lower the entropy, and vice versa. Greater disorder, the greater the entropy. All right. So entropy is a state function. We'll talk about that later on. But basically, we can determine the change in entropy, which would be the final entropy value minus the initial entropy value for a process or a reaction. All right. Um, so if the change of initial to final results in an increase in randomness, that means that the final value of the entropy for that process would be greater than the initial. In other words, delta S would be positive. On the other hand, if it's a reverse, if the change from initial to final corresponds to a decrease in randomness, then delta S would be negative. So, as an example, if you take any substance, right, one can see, based on our knowledge of how atoms are arranged in the solid, liquid, or gaseous state, we can therefore come to the conclusion that the solid state is more ordered than the liquid state, which in turn is more ordered than the gaseous state. All right? So basically, the entropy of the solid would be less than the entropy of the liquid, and the entropy of the liquid would be much more less than the entropy of the gas, because the gas is more disordered. The liquid is not as disordered as the gas, but it has some disorder, such that its entropy would be greater than the solid, which would have the least amount of disorder. All right, so that's how we can apply the term entropy to a substance existing in different phases. So if you look at the transition of H2O solid to liquid, in other words, melting, then of course delta S will be positive, because the water in the liquid state would be more disordered compared to ice or H2O in the solid state. So therefore delta S would be positive for this process. All right. So basically, these are some examples of situations where delta S would increase for these processes. Going from solid to liquid or liquid to vapor, as you can see, obviously, you're going from a more ordered system to a more disordered system. Going from a solute plus solvent to give a solution, that also increases in disorder. And even if you have no chemical reaction, but let's say you have a substance at a temperature T1, and then you increase the temperature to T2, where T2 is greater than T1, the system at T2 would be more disordered compared to the system at T1, because the particles would have a greater amount of energy, more vibration, more movement, and therefore more disordered, and therefore greater entropy. All right. So that basically, these are just some physical processes where you have an increase in entropy taking place. All right. So based on this, we can answer this question: how does the entropy of a system change for each of the following processes? Condensing of water vapor. Well, if you think about it, water vapor is in the gaseous state, and when it condenses, it goes to the liquid state. So therefore, you're going from a more disordered system to a less disordered system. So therefore, in that case, delta S would be negative, all right, because entropy decreases as you go from the liquid state to the, from the gaseous state to the liquid state. Okay, forming sucrose crystals from a supersaturated solution. So we're going from a solution to the crystals, which are solid. So we're going from a more disordered system to a more ordered system. So again, the randomness will decrease, and therefore delta S would be negative. All right. Heating hydrogen gas from 60 degrees to 80 degrees. Now, in this case, you're going from a lower temperature to a higher temperature. So, as we said before, when that happens, the molecules will have more movement associated with it. So, therefore, there's more randomness associated with that process. So, therefore, randomness increases, and therefore, delta S would be positive. The last one, subliming dry ice. So, I don't know if you know what sublimation is. What sublimation is where you have the conversion of a substance from the solid state to the liquid state. And dry ice, which is frozen carbon dioxide, will do that under normal room temperature conditions. So here we're talking about a situation where we're going from a more ordered system to a more disordered system. And therefore, as a result, the randomness increases and therefore delta S will increase. So these are just some examples of physical processes where delta S can be actually predicted in terms of whether or not an increase or decrease will take place. All right. As far as entropy is concerned, more specifically, it's a state function, just like enthalpy and energy and other state functions that you would have met before. All right. And one thing about state functions is that um, there are properties that are determined by the state of the system, regardless of how the condition is achieved. Right. So therefore, it doesn't matter how you get to, let's say, 25 degrees for a substance. The state function that determines its properties, it could be enthalpy, it could be entropy, will be a particular value at that temperature, regardless of how you arrive at that state. And the illustration shown here basically um, is illustrating the whole idea of state function. If a hiker from this point here travels this pathway to get to the top of the mountain, and and another hiker choose a more, complicated route. They both get to the same peak. That means that the difference between, in terms of height, between here and here is still the same. So the net result would be the same for both hikers, even though one traveled a longer distance. It's the same idea with state functions. It doesn't matter how you get to a particular state function at a particular temperature, pressure, etc. The state function value will still be the same. Okay, so entropy is what we're concerned with, and entropy is a state function. And over here, before I leave this page, we see a table here which gives you a few substances and their entropy values. All right. There's a more comprehensive table that is present and available in Canvas under the tables folder in the file, under the files link in the tables folder. So that's a table that you should refer to when it comes to obtaining entropy values for calculations. Okay, I'm going to stop here. The next topic I'll be discussing would be the first law of thermodynamics, and then we'll move on from there. All right, until next time.